somebody can check that we are streaming, I would appreciate this. Все как надо, систему названием КПТ. Хорошо.
Не, да, я говорю, городец файл.
Вот именно название?
Да, нет, не про наш. Нет.
Давайте выключим тогда еще раз.
В смысле она с нуля началась? Ну давайте попробуем. Вообще должен.
Нет, если сейчас градиентов стримится, то значит...
Но оно как бы стримится градиентов, но, видимо, лекция его не записана или записалась тоже под другим именем. То есть он только началось.
Нет, градиентов там по другим названиям тоже стримится.
То есть он не делал того, что мы сейчас делаем?
Ну, видно.
Неужели она максимально близка к идеальной? Лучше не сделать.
Кстати, у тебя точно?
Давайте начнем.
Okay. So may I have someone's? Yes, thank you. So we have two lattices. One is generated by the roots. And another is just some just this. Yes. Okay, so the idea of the proof is to have this lattice to be generated by some nice elements. What we will do for this? We will have some elements beta I such that this thing is 1 when alpha equals alpha r and when alpha equals alpha I, and 0 otherwise.
So it's like
I will alpha j. So it is easy to see that these elements will generate this lattice if we have these equations. Yeah, so
beta E some scalar multiplication to scalar multiplied by alpha E.
no, it's not like that because yes. So the idea is to have some beta I prime that is in the orthogonal complement to the elements alpha I without I.
Sorry, what is
Beta I it is not yet defined, but we will want to have this.
I think they are uniquely determined.
Yes. So okay. So we have.
So it's a base, right?
It's a basis, and this is a theorem, a claim, even.
Yeah, the claim is that the basis for
Well, this arrow is obvious, right?
Yes, and this one. So we will think that it is also obvious. Okay. So after this, we will prove one more equation, that alpha i's are nicely decomposed into beta i's, beta g's.
What do you mean nicely?
What do I mean by nicely? That coefficients are alpha I, alpha j. Maybe the other way around, but we will see. Okay, so we can. Beta is this. This.
What are the indices?
And alpha I, alpha j. The one alpha I. Yes. So. Okay. I did not. I just have a claim that I will prove. Yes. So we can have have an inner product of alpha i's and alpha j's.
So we kind of want to say that the matrix for change of basis from alpha eta to beta eta is just Cartan matrix, yeah?
I want to say that that the lattice P is just a lattice in Q that is generated by an alpha I alpha j. Okay, so we want this, and we will just replace alpha I with this equation. And we will compute it. So this is yes, the indices are not correct because I want this to be different from this j.
Yeah, but I mean that should be 2 alpha I alpha j quotient.
Oh yes, yes, it's right. And this delta, yes, this is correct, I suppose. Yes. So this is sum of delta jk alpha alpha j. Why is this so? Because wait a minute. This is the claim, and I want to show it.
No, that's true just because of how beta eta is defined.
Yes. Yes, because I'm too near the desk. I don't see everything. So okay, this is true. 2 was is in beta I, in the definition of beta I.
I guess you just want to see that the guy with alpha is 2. Wait, it's alpha j divided by 2, and that's why 2 is gone.
Yes. So this is alpha I alpha k. And we see that alpha is a basis, so if we have these the same, so this claim is proven.
No, I'm sorry. I think I lost it. So then just plug in what you would like to prove, right?
So
this is the question mark, okay?
yes, да.
So you start with this one and see that it is like that.
Yes.
And here just use definition of an alpha. Yes, okay.
So yes, so we have this decomposition. We have if we watch P and Q from the point of view of basis beta, P is just z to the power of n, and Q is generated by vectors n alpha I alpha j. So it is true that it is true.
So we're proving the determinant of Cartan matrix equals to P over Q.
Yes. So yes. Yes, yes.
But actually not up to the sign. Well, we
I
would
suppose.
like to prove up to the sign, but it's actually true. I think
What we
without even
what we say up to the sign isn't it just amount of elements? Or what is it?
But determinant can go.
Determinant. Yeah, of course, determinant.
determinant can be negative, right? But it's actually not negative. The Cartan matrix is positive. I don't know if
So
it's easy to check right in 2 lines, maybe not.
So why after this statement we understand that the proposition is true? Why is this equal to the?
Yeah, can you repeat please?
Yes. So if basis is beta, then Q is just integer lattice, and P in this integer lattice is generated by vectors n alpha I alpha G.
Should be just.
Oh yes, yes, of course. Some z n alpha I1 and alpha I alpha n, something like this.
So you make a transformation such that your betas now are just standard, not just standard basis, right?
Yes.
And fundamental area for Q is spent by your alphas, which are some bit, right?
Yes.
Right. With actually such coordinates.
Yes. So this statement is then obviously true. Because we have this claim of lattices when this is a standard lattice and this is lattice generated by some vectors. This because we can change the basis, and this will become a standard lattice, and this will become a lattice generated by these vectors. And since the change of basis doesn't change this number, this is the same.
Yeah, I think what
It looks like
this
it's
thing
kind
is
of
that like that's something that everybody learns in kindergarten.
Yes.
I forgot how to draw it.
About lattices, right?
Yeah, I forgot how to draw it.
Yeah. So I don't know if somebody has a better explanation, but I think so. What I learned maybe not in kindergarten, but a little bit later, is that determinant of such kind gives me a volume, right? So this we all can believe, right? so if I have like a two alphas, right? So this is a volume. So I make my, sorry, this is not volume. So my beta i's, which are usually actually omegas denoted in representation theory, are this, right? And I have some something something that is like a parallelogram, which is spent with sides which are roots, right? So alpha 1, alpha 2 in this case, and this is like beta 1, beta 2.
But really doesn't get why it's determinant of this matrix and not the inverse of determinant, because like we like B is something larger and Q is something smaller, isn't it?
No.
Q is a
actually
subset.
Like this is the fundamental domain of Q.
Yes.
So Q has less points, right? So these are just some points of P. So for fundamental domain is larger. So what I'm writing, like determinant of like n alpha I alpha j is the volume of this thing. In what units? And this is the unit, right? So this is exactly how much fundamental domains of the smaller lattice is inside fundamental domain of big lattice. I don't know if this was more convincing or not.
I mean, is
Maybe
there
more
like
convincing
some?
or not enough. Sorry.
I mean, yeah, I believe in fact, but I just wanted to have like some
So
rock solid proof of it.
rock solid proof of why the determinant of, so if I have a bunch of vectors, right, in standard basis with coefficients ai, maybe like j, like this is these are I don't know, like should be like something like this, right? And I am computing determinant of AJI, right? Why it's a volume.
No, this I believe. Like why?
Okay. Okay, so then.
I still like okay.
So now
Intuitively,
next.
I understand it.
Yes.
But how do we go from volumes to actual elements of the quotient?
We can have a really, really big sphere, and we will, if the radius goes to the limit, the number of points in the sphere is, not in the sphere, in the cube, it will be better. The number of spheres in the cube that are in one lattice and in another, this fraction is going to go to this because of the volumes.
So I'm sorry. So your when I say fundamental domain, does it make sense, right? For lattice. Okay. So then I'm saying that if I have lattice and sublattice, then the order of this group is exactly the ratio of fundamental domains.
Yeah.
Of volumes of fundamental domains.
Okay. Yeah, I remember. Okay, now
This is clear because like this is exactly if you take fundamental domain of bigger thing and quotient it by the smaller lattice, it's exactly your like points, like your class of like equivalence class under this quotient will be exactly small fundamental domain. Right? So how much small fundamental domains in bigger fundamental domain is exactly this number.
yeah, okay.
I cannot say.
So do we have it here number of integer points?
Yes.
Domain.
Yes. Well, just because we, yeah.
It's not obvious that it equals to the volume. So
Yes, it is not.
Have some proof of this
Yes.
asymptotic,
Okay.
but it's not obvious.
So you have proof?
It is just if we have a really big cube and it expands, then the number of points, then the quotient of number of points of this is going to be the quotient of volumes.
But I don't know. For me, domains are convincing. I think I cannot say.
Domain have X, the formula T,
Mm.
but it's obvious that it works. But in higher dimensions, we don't have such formula. We have a theorem from algebra that if we have a lattice and a sublattice, then we can choose basis that agree. A basis in a lattice and a basis in a sublattice, such that
Yes, that's normal smooth form. That's a
yes,
good
yes.
idea.
And if you use this, then this is obvious. In what sense do they agree? If we choose, we can choose a basis in a lattice such that there is a basis in the sublattice which is roughly saying a multiple of the basis in lattice. We multiply the first vector by some number, the second vector by some other number. Okay.
Yeah, this gives rock solid.
So yeah, I don't. Well, this alphas then is not a good basis for Q.
Yeah, but
I just need yes. I just need
Yeah, because the determinant doesn't change if you add something to the string, yeah? Namely the other string multiplied by some constant. So in this case should be integer. But
yeah, but this argument is
yeah, this is a good answer.
okay. Thank you. What was? About this. I think Mark, you want fifth?
yeah, because
Okay, sure,
I don't
sure.
really have
Sure. Okay.
a
So
great solution for this one. It's
then,
kinda
okay, one. You can show the solution. Second. Maybe we should make a rule that this list, then you can only put number like problems which we didn't discuss.
We still have to upload the solutions before the seminar starts, so I don't.
Yeah, that's true. But maybe a solution is not.
But then you will see, right? While checking.
Well, I'm checking. So this particular that I'm checking is that
Really?
nothing catches my eye. Like no.
Okay. Well, let us begin with problem
So
2.
it's not a high quality. Good to know.
Well, we know that E and E star are isomorphic. They're canonically isomorphic by the form that exists on E. And let us fix such an isomorphism. This isomorphism, we denote this by phi. And how it looks like? It looks like this. Phi
phi of v applied to u is maybe we denote it like this. I don't remember. And since
What is this scalar product? Is it divided by? Is it just usual scalar product?
just usual scalar product. E is a space, is a Euclidean space.
If it's divided, then I think it's not interesting. It's just the same root system. This root system is a root system which corresponds to the algebra, which is usually called Langlands.
And from our definition of lambda, как произносить это? Lambda check, we have the following. We have phi of lambda is lambda 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 check over 2. And I will use it. So I want to fix this formula. And now first we need to check that alpha 1 check, alpha 2 check, etc. Denote this by a check is a root system. So we need to check all the axioms of root system. So first it is clear that these guys generate E star because phi is an isomorphism, and we know that they're still linearly independent even after we multiply them by lambda lambda over 2. So we can view our map lambda from lambda to lambda check and be viewed as a composition of phi and multiplying by some numbers. They depend on vector, so it is not linear, but it doesn't spoil anything. So the first axiom is clear, and the second axiom, we need to see why this is integer. By definition, this is 2 alpha check beta check over beta check. And if we apply this formula, we can write this like this. 2 multiplied by 4 alpha beta divided by alpha alpha beta beta divided by 4 over beta beta. We need to apply this formula. Well, and we need to say that phi is an isometry. It preserves a scalar product just by definition. So we can write something like this. Phi of alpha, phi of beta is alpha beta. And then we substitute phi of alpha with this, and we obtain exactly this formula. That alpha check beta check is 4 alpha beta divided by alpha alpha beta beta. These guys cancel, and we obtain this. And this is exactly n beta alpha. And it is an integer number because R is a root system. Next, we need to check that for any alpha beta in R, this guy divided by alpha check lies in A check. And we don't know it yet here, we want to check it.
Yeah, because this is not a vector, the second sum.
I forgot to write alpha check, yes. Now it's correct. Okay, we just we are just going to show that beta minus 2 alpha beta over alpha alpha alpha. Yes. Check.
Yeah, again, alpha.
Alpha. Yes. It's exactly this thing. And how we are going to prove it? We are going to apply it to an arbitrary vector mill. Well, we know that R is a root system, so this thing is a root. So this thing lies in a check. And if we apply, then by definition we have the following. We have 2 beta mu minus 2 alpha beta over alpha alpha by 2 alpha mu divided by the scalar product of this thing with itself, but it is exactly beta beta because this thing is actually as alpha applied to beta, and as alpha is an isometry. So as alpha of beta, as alpha of beta is beta beta. So I write it like this. This can be rewritten as 2 beta mu over beta beta minus okay, minus 4 alpha beta divided by alpha alpha beta beta. Alpha mu. And also we can check that if we apply this thing to mu, then we obtain exactly the same thing. Let us do this. Divided by alpha 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 check alpha check alpha check applied to mu. Then we need to apply beta check to mu, and this is exactly 2 beta mu divided by beta beta minus, and here we again use this formula to rewrite alpha check beta check alpha check in terms of alpha and beta, and this must be something like this: 2 multiplied by 4 alpha beta alpha alpha beta beta divided by 4 over alpha alpha, and then 2 alpha mu over alpha alpha. I hope I didn't forget anything. And then these guys cancel, and we obtain exactly the thing. So this guy and this guy acts on mu in the same way. We have 2 multiplied by 2, and this is 4. We have alpha beta, we have beta beta, and alpha alpha. Yes, we already checked that this is a root system. Okay. It was not part of the problem, but it is true. Yes.
Yeah, but this
maybe not so.
Wait, the image is proportional. If two vectors are proportional, then the images are proportional.
Yeah.
The proportion is the same.
Yeah.
Well, we have vector t in E defining a polarization of our root system. Then we can say that t checked in E check also defines a polarization of A check. And this polarization agrees with the old polarization. This means that if alpha is positive, then actually alpha is positive even only if alpha check is positive.
Star, right?
It doesn't really matter here.
What?
Oh, what is T-check?
Scale
T-check.
for T-star.
T-check.
T-check, it means that on each, E-check. Okay.
Yeah, E-check and T-star.
And of course, but this is just because this map from lambda to lambda check, it does not preserve the scalar product, but at least it preserves the sign of the scalar product. And we have the set of simple roots. I do not remember what was the last index.
Usually R because it's rank of
R. Let it be R.
but doesn't really matter.
Then it is sent to alpha 1 check, alpha 2 check, alpha right check. We already know that it is a subset of R plus check. And in order to show that okay. Okay. And I want to say the following. I want to say that simple roots are uniquely characterized by the following property. The simple roots are just k positive roots, are positive roots, such that if we consider the convex polyhedral cone generated by these roots, then all positive roots lie in this convex polyhedral cone.
Maybe you can write.
Well, claim, I will say. Suppose that we have beta 1, beta 2, beta r, which lie in A plus or A plus check. It is true for both root systems. I will write A plus. Such that the following condition is satisfied if we consider, I guess it is written like this. This is the convex polyhedral cone generated by beta 1, beta 2, beta r. And we just take all linear combinations of beta 1, beta 2, etc., beta r with non-negative coefficients. In two-dimensional case, it is something like this. We need we need that all other positive roots like here. For any beta in A plus. Then I claim that beta 1, beta 2, etc., beta r are simple roots.
So it's like for others not simple, well chamber should be something small.
Yes, I guess it is something kind of it, kind of this. And
So you're claiming that it is obvious?
well, we can say the following. Suppose that we have beta 1, beta 2, etc., beta r that satisfies this property. satisfy this property, then clearly all beta 1, beta 2, etc., beta r are simple. I guess it is some statement from convex geometry. Well, we have a convex polyhedral cone such that all these R roots lie on the border of this cone. And all other positive roots lie somewhere inside the cone. Well, these roots, beta 1, beta 2, etc., beta r, form the edges of this cone, in fact.
So it's like they can't be a sum, because the sum will be between.
Yes, yes, I think it is some statement from convex geometry. We cannot obtain any vector line on the edge of this cone, summing some vectors from some other vectors from the cone.
I think in a sense it's a dual statement to the statement that the positive Euler chamber has walls of hyperplanes that are perpendicular to
Yes, I think it's true, yes. Mhm.
Yes, but for
Not actually, because there you just take the roots.
you already have simple roots there. So you're proving.
No.
No, the statement is that if you take the simple roots, then if you take the convex half of it, right? If I
Yes.
understand
Yes.
you get all the positive roots, right?
No, the statement is
And the statement
some
is the converse.
roots like that, such that their convex house contains all positive roots.
Yeah, that's a
Then they
convex,
simple.
It is a converse statement. It can be viewed as a converse statement. But, okay, if beta 1, beta 2, etc., beta r satisfy this property, then beta 1, beta 2, etc., beta r are simple. And there are only r simple roots because they must form a basis of E.
If we have for this set of roots just sum of beta 1 and beta 2.
There would be too many vectors in the system.
Yeah.
It is important that I take exactly r roots here. Yes. Yes, it is important, yes.
But now the statement is important.
So it's believable, right?
Okay, let me
Yeah, okay.
let me say it again.
Suppose we believe that.
I think if these roots are linearly independent, then
They must be linearly independent if they satisfy this property. If they are not linearly independent, then their linear span is not the whole E. And then we will not obtain the whole R, R plus. Again, let me repeat briefly. If beta 1, beta 2, etc., beta r satisfy this property, then they're all simple. And there are only r simple roots because simple roots form a basis of E. So there are no other simple roots. So I guess it's okay. Okay, now the statement is more or less clear. Our statement which we need to prove. We have alpha 1, alpha 2, etc. alpha r in R. In E. And they are sent to alpha 1 check, alpha 2 check, etc. alpha r check. And now let us recall how this map check is defined. We can view it as a composition of the isometry phi and multiplication by some positive numbers. this positive number depend on the vector, so it is not a linear map, but at least it preserves convex polyhedral cones. So for alpha 1, alpha 2, etc., alpha r, we know that the convex polyhedral cone generated by them contains all positive roots. And this property is preserved by our map check.
So up to, yes, up to this claim, which is,
But what is wrong with this claim?
It's clear.
Yes.
yeah, okay.
Maybe the first part was not completely clear.
No, I'm still trying to see how to prove this, like, not referring to. Okay. No, it's okay. Thank you. All right.
I did just like if we have alpha beta check the sum of some roots, then we have that alpha beta is a alpha plus b beta, where a and b is some rational numbers. Yeah, and it's just dots because we have we classify all reduced root system, and reduced root system is just dot concept.
Yes.
So I did like that.
Yeah. So it's actually this problem also appears in Kirill, and he suggests like the hint that he uses what you explained.
He suggests thinking about it in terms of Weyl chambers. I didn't say these words, but I guess it's something like this. Yes.
So because like so maybe let me also write it. So if you have alpha check is beta check plus gamma check, right? For some positive alpha beta and gamma. It actually means that alpha divided by alpha squared. If you write this down, it means this. So you have to have three vectors of the same length. One,
Why is it? Okay, yeah.
which one is the sum of the
Divided by square of norm or by norm.
Yeah, so that should be square.
But then the length is not.
Yeah, it's kind of not true that the length is one.
yes, if I divide by square, then
Yeah, it's not
okay, then I'm
so yeah.
yeah, so then my yeah, so I thought that the only angle that can be is 60 degrees. And yeah, at least that's square.
Could you just also just explain?
Yeah. Okay. All right. Thank you very much. So, yeah. Number 3 then. Okay. Nikolai. I'm kind of out of any order now. Just give me somebody who I didn't like. I don't remember too much. Yeah. The last. It means last one.
The first claim is that let us consider such set. It is an open set and I claim that C plus is one of the connected components of E prime, and it is quite obvious.
Isn't we improved? Let's see plus
Alpha R. Okay, I see.
And what are connected components of such set? All connected components of E prime are of the form we already have discussed this of the form where alpha eta are here and delta I is plus minus 1. I don't claim that every such set is non-empty, but if it is non-empty, it is a connected component, because we can't соединить 2 points from different such sets, but and of course they are open. And let us take delta I equal to 1, and we get C plus, because such every element from this is so I since every element from R is a sum of alpha y for some natural non-negative. So it is clear. And now I would like to formulate 3 simple lemmas from which all statements will follow. Lemma 1. First, I would like to give one definition. Let S be the set of such Weyl chambers that can be derived from C plus by simple reflections. And let R prime be all roots that can be derived from simple roots by simple reflections. And the first lemma is if alpha is in R prime, then S alpha is a composition of simple reflections. Then if alpha and beta are in R prime, then such a root is also in R prime, and for each alpha from R prime, S alpha is a composition of simple reflections. But it is a really simple statement, because let alpha be as alpha I1, the alpha I j's are simple roots. Then S alpha from then S alpha G is simply, let's call this W as alpha J and W inverse. We have proved this on the lecture. But what is this? W prime is these reflections, but written in the inverse order. Then the second statement, since beta is a composition of simple reflection, since beta is W from some alpha y, where W is a composition of simple reflections, and S alpha is a composition of simple reflections, then of course no, we simply write this. It is and of course it is a composition of simple reflections.
Isn't 3 is just 1?
No.
Why?
It is one inverse. Excuse me.
No?
Yes. So we. Yeah. So we really don't need even 3.
Okay.
And
Okay. Are all roots that we can get by simple reflections from simple roots, right?
so our goal is to prove that R prime is R. And
Yes.
lemma 2, it is very simple. If C1 and C2, they are Weyl chambers, are adjacent and share a face which lies in L alpha, where alpha lies in R prime, then C and C1 lies in S, then C2 also lies in S. It is really simple because since they share a phase which lies in alpha, then C2 is S alpha from C1, and S alpha is a composition of simple reflections by lemma 1. And lemma 3 if C is a Weyl chamber such that all walls of C are of the form L alpha, where alpha lies in R prime.
C1 lies in S.
It is assumption.
So
For example, this property holds for C++. Then all adjacent Weyl chambers with respect to C also hold this property, and it is a key lemma.
Okay, so if
Proof. Let C prime and C be adjacent. Then and L gamma prime is a wall of C prime.
gamma prime is S
So we have L gamma prime is a wall of C prime, and I would like to prove that gamma prime lies in R prime, but L gamma let L beta be the common wall, and L gamma prime is S beta from some L gamma, since C prime is S beta from C. And we also know.
can you explain this lemma third for something like C2? Like, can you just
C2 is
I suppose it's like have two simple roots and one alpha plus beta.
for this?
This is A2.
No, it is no A2.
A to find also. Yeah, yeah.
Oh, okay. So we have
So C plus is this one.
this is C plus.
Yeah. And adjacent to C plus, it's
Oh no, it is not C. So what this is? This is C plus. So we have such two walls. This one and this one are of this type, of this. And then I prove that
Reflect.
the reflect, well, for example, this one is also of this type.
Can you mark what's
So
here?
so this is C plus, then I can consider, let it be C. Then I can, we can,
C prime is also this form,
yes,
but is it?
It's almost obvious.
it's almost obvious,
Yeah.
but
Yeah, why is it of this form? Like, isn't it, like, we have these both are simple roots, yeah?
yes.
And this wall
But this wall is not the wall of the
Yes.
simple root.
this is not a wall of the simple
Yes,
root.
but it can be obtained.
By applying simple reflections to simple roots.
R prime
So
is,
that's what
That's what
or
you mean.
But R prime is actually everything. So it's hard to give an example, just take any example.
Yeah, okay.
Yeah.
and gamma lies in R prime, so as gamma prime, so gamma prime is simply this.
No, the only thing here is that the walls of C prime is obtained from the walls of C by the
Yeah.
reflection respectively, like wall that they share.
We have such, and so gamma prime lies in R prime by lemma 1 part 2. So we have proved this lemma.
Okay, so now we should look at three lemmas and everything.
Yes. So we
But what everything? What we're trying to do?
firstly, I would like to show that S is a set. S is a set of all Weyl chambers, and R prime is R.
Okay.
And let us consider such Weyl chamber C plus. It holds this property. So every adjacent Weyl chamber also holds this property. But we have proved that from any Weyl chamber to any, we can go through adjacent Weyl chambers.
Yes. All Weyl chambers
So
actually possess this
all,
property.
yes, and since for every alpha in R prime as alpha lies is a composition of simple reflections, we can conclude that if C lies in S, then all adjacent and holds this property, then all adjacent also lies in S. So all Weyl chambers lies in S, and R prime and all their walls lies in S, in R prime. So R prime is R.
Yeah, R prime is R. S is the whole is the set of all Weyl chambers. It means that R. Yes, it's exactly what we need to. Yes, it's exactly what we need to.
Yes.
Okay. Yeah, thank you very much. So this means.
Can you explain a little bit why our prime is so why is that property?
So
Because we start from C plus, then we can go from to any Weyl chamber C by adjacent.
Yes.
Every neighboring Weyl chambers are adjacent. C plus holds this property.
Yeah.
So C1 also
CK
holds.
this
So CK.
And that's the first statement of the proof. What about the simple reflection generate Weyl group and
So what we have proved that if this in R's S and holds this property, then this also lies in S. by lemma 2. Then this also lies in S and holds this property, but what this means that alpha for any alpha in R is a wall of some C. So alpha lies in R prime.
That R prime equals R is exactly that W of P is R.
Yeah.
Yes. Then simple reflections generate W.
Yes.
It follows, I think, from lemma 1.
Yes. Yes. From the first state. If alpha lies in R prime.
Yeah, of course.
Yes. Okay. Seems like it's a lot of lemmas, but that's okay. 4. You have 4 people in an uncertainty, so you can go this way or this way. No.
No.
With Nikolai.
3 and so.
Yeah.
Okay, so I'll also start with lemmas.
5 lemmas.
Well, no, there will be like 2. So,
Just keep in mind that we have 4 maybe 1 minute, but
yeah, so first of all, I want to show that in case R is an irreducible root system, right? Then, well, let's say I fixed the polarization already. So the set of simple roots will be denoted like this. And the first thing I want to show, well, I want to show that alpha 1 plus alpha R is inside this root system in case R is irreducible. So, first thing that we have to notice is that we have 2 roots, alpha and beta, such that the scalar product of that is less than 0. Then alpha plus beta, now maybe from R plus even, then alpha plus beta is inside R. So this can be checked by just, well, I'm not going to prove it. I just want to say that it's enough to check it for 2-dimensional root systems, because all you need to check, because this vector lies in this 2-dimensional system that is generated by alpha and beta. So, well, actually, I will only, yeah. Well. So, okay, now I have to.
I think it should always be non-positive.
What?
Right? So,
This?
yeah.
No.
Two simple roots.
Well, let's say we have a system.
The cell is simple. Yeah, there's no simple. It's just some positive.
For the simple roots, it still can be that it's equal to 0.
Yeah.
But, well, it's the second proposition that I'm going to prove right now, is that if, oh, sorry, for some reason I wrote in Russian. Proposition 2 is that if we have 2 simple roots, then just, well, then the scalar product of them is less than or equal than 0. Well,
We proved it like in the lecture.
we didn't prove it.
Yeah, but it's also the statement from classification of the root system.
Well, if it's obvious, I can just skip it, right? Like, okay. Okay, very nice.
But
So should I prove it or not? Like,
No.
no? Okay. My proof is just assume the otherwise, then the scalar product of alpha 1 and alpha 2 is, and minus alpha 1 and alpha 2 is less than 0, then the sum lies inside a root system. That means that either alpha 2 minus alpha 1 or alpha 1 minus alpha 2 is a positive root. And then you can sum it with the alpha 2 or alpha 1 respectively. So we get alpha 1 or alpha 2 as a sum of two positive roots, but they are simple, so it's in a contradiction. Okay, so this is my. Okay, so now statement. Now statement. So let's assume that there exists such permutation sigma such that of simple roots, sigma permutation of simple roots such that for every index I, sum of k equals 1 alpha sigma of k alpha sigma of I plus 1 is less than 0. Well, we know that this is just a sum of scalar products of some simple roots, so it's obviously less than equals than 0, but I want one of these summands to be strictly less than 0. So I assume that such permutation exists. And I say that if this permutation exists, then it's obvious that the sum of all simple roots is a root. Why is that? Why? By property 1, essentially. Because, well, what I will prove, I'll just prove by some kind of induction that I'll never form as induction. But, well, let's say, what does it mean? It essentially means that, well, I want to prove that in this case, if such permutation exists, then the sum of simple roots is a root.
So like I should be lesser than R. Should start from R minus 1.
Yeah. Yeah, well, this means just that there exists k that is less or equal than I, such that the scalar product of alpha sigma k and alpha e plus 1 is strictly less than 0. Then all others are strictly less or equal than 0. This is less than 0. And this gives us a proof. And obviously, one of these summands has to be less than 0, because if all are 0, then the sum is 0. So these are indeed the same statements.
Yeah, so say like for any simple root, there exists simple root that not orthogonal to.
Yeah, that is yeah.
Oh, okay.
With the last number. So now let's say that this permutation fixes the indexation. So now sigma of k is k, and just so I don't want to write extra stuff.
Suppose now.
Well, yeah.
Now we just take like e equal to r minus 1, and that's all.
Yeah. Well, now we just say that. Well, first of all, this statement means that alpha 1 scalar product with alpha 2 is less than 0. And just by the definition that I've maybe. Okay. So, and that means that by proposition 1, alpha 1 plus alpha 2 is in R, right? But then I want to assume alpha 1 plus alpha 2 and alpha 3. Well, here I forgot to mention that alpha and beta should be they should not be collinear. But this is actually I fixed because I said R plus and they're different. So, well. Okay, so what
Isn't it already obvious? Can we just take I equal to the R minus 1?
well, you need to check that. Well, I just do it step by step, right? I just say that this is a root, then this is a root, then this is the root. Well, this is a root because, well, because these two are less than or equal than 0, right? So this is alpha 1 plus alpha 2 plus alpha 3 is a root. Again, by our proposition 1, and it goes further, and we obtain that alpha 1 plus alpha r. Oh, sorry, it's not true. Like this. Okay, so now, but I assumed some condition when I stated it. And now I want to show that this condition is exactly the condition of irreducibility of R. Well, first of all, let's understand what does it mean. Let's draw a graph where the vertices are the roots, and we have an edge between vertices if the scalar product. Okay, if two roots are wait, what? Non-orthogonal. So the scalar product is less than 0.
Yes.
And I claim that this means if we don't have this permutation.
You started drawing Lincoln diagrams.
Not really, but yeah, almost. Well, this diagram is a lot less complicated than the Lincoln diagram. Well, so. And if they're not orthogonal, well, there is some graph, right? And I claim if this graph is connected, then I can always get this permutation. And if it's not connected, then there will be some extra steps. Okay, so this graph is like the vertices are exactly the roots, the simple roots.
What do you do if the graph is connected?
If the graph is connected, I get a subsequent tree of it. Then I fix the vertex, some vertex, and by this vertex I can look at my graph the following way, right? And then I take this is the first, this is second, this is third, this is fourth, this is fifth, this is sixth. So for each vertex, I have some vertex that is connected to it, and its number is smaller, because I move by my tree to from обход графа, короче, делаю.
Yeah, but you look at some scalar product with sum of roots.
No, again, this is some root alpha 1, let's say. And this is some root alpha 2. This edge exists if and only if, like this edge, if alpha 1 cross alpha 2, I mean product with alpha 2 is
Less than 0.
yes.
So
Or not 0. These are only simple roots.
Well, they are simple, so there cannot be positive.
okay, it's simple ones.
Yeah.
Okay, you just didn't say. Okay.
No, I said alpha 1, alpha 2. There is a permutation of simple roots, so these are simple roots. So the vertices are simple roots. Okay. Okay, so you believe me now that if the graph is connected, then we get this permutation, right?
So connected,
Well,
okay, but how?
Well, if the graph is connected, there is a subsequent tree. I mean, subgraph as a tree, right?
Right.
And, well, I get this tree. I take some vertices. I don't know how to say it in English, but подвешиваю graph. Well, I just assume this is a top vertex. And then I just take it on the first level, all vertices, then on the second level, by the third level. Yeah, it doesn't matter how I number the vertices on the same level. It doesn't matter. I just have to, well, because each vertex on the next level is connected to some vertex on the previous level, and its number is obvious.
Less than 0, yeah, for sure you got something less.
Yeah. So okay.
Yes.
So I get this permutation. Okay.
Yes.
Well, but what means that the graph is not connected? It means that it has at least two connected components, right? Well, let's say that we have two connected components. If there are more than two connected components, then just say that all components except for two are like in one component. Well, just make it two connected components. Well, well, then we get P is P1 connected with P2 such that each vector from P1 is orthogonal to each vector of P2. well, now I claim that by lemma 3, or no, not by lemma 3, but by problem 3, yeah. This thing is, well, this is not by problem, but by just a definition, right?
No, it's kind of the statement.
This one.
Yeah, it's kind of the statement that
No,
you can't, that you, if you have two orthogonal.
No, this is just action of group of Weyl group on some
Yeah. So
this is not a statement
no,
because these are just an elements of the set,
Yeah,
and if you act on them,
orthogonal, you should say this.
yeah, it requires checking that these things are orthogonal. In fact, it's actually root systems in some vector subspaces will also show it. So okay, I think this is.
It's just vector subspace that's induced by P1 and induced by P2.
Yeah, true. Yeah, you just take the linear span. So let's prove that these subspaces are actually orthogonal, right? Not subspaces, but these subs.
Do you need it?
Yeah, because it's well, yeah.
Isn't you already proved everything?
I haven't proved that they are orthogonal.
No, I think about the proposition form, problem form.
I haven't proved the problem 4 because I have to show that the R is irreducible in that case, but to show it that it's reducible, I have to present two subsystems. I have to present some
I understand.
R2 and R1. This is not the whole, like, right? I have to present because, well, P is not equal to R, right? So the definition of irreducible system is that I can. Reducible system is that I have R1 and R2 such that R1 is orthogonal to R2 and R1 with R2 is the whole. Yeah, so I want to show that this and this, like, well, it's obvious that, well, this is by problem 3, right? So I have that they are, well, I don't really have that they don't intersect yet. It also requires checking, but I have that the union of these sets is exactly R, right? I have to check that they are orthogonal. If they are orthogonal, they obviously don't intersect, right? So I will get everything by just proving that these things are orthogonal, right?
It's not almost there. We're almost there, right? So
Yeah.
just
It's a finish.
Yeah. Well. Yeah. Now I just need to show that. Well. Let's denote V1 as a span, linear span of P1, and V2 the similar way, okay? Just for P2. Now I claim that, well, that's an obvious claim, that V1 is actually, well, first of all, E is V1 plus V2, and V1 is orthogonal to V2.
right.
This is just because these are bases, right? And the bases are orthogonal, and they span the whole because P1 is the union, P is the union of P1 and P2. Okay, so the only thing that is left to check is that, well, now I want to finally state this, that if P1, I have some notation here, well, P1 consists of B simple roots BIs, like let's say B1, BT, right? And this consists of what? Well, some gamma i's. So the simple roots here I will call gammas, simple roots here I will call betas. Okay, so I claim that V1 is an intersection of all these hyperplanes. Well, that's kind of obvious, right? Again. Okay, so and V2 is intersection of this. Well, but if it's true, then it's obvious that simple reflections. What do simple reflections do? We only need to actually check what are the simple reflections, because what we want to understand is that actually if we take any element from V1 and apply some element of a Weyl group, then we get to V1 again, right? And if it's and the same for V2, and if it's true, then it's obvious that V of P1 is orthogonal to V of P2 because, well, they're in V of P1 is in V1 and V of P2 is in V2 and they are orthogonal. Well, why is it obvious now that V of, like if we apply any element of a Weyl group to V1, to some vector of V1, we get a vector from V1. Well, because we only need to check it for the simple reflections, and the simple reflections of the form S gamma I, what do? They do not even do anything for V1, right? And reflections of the form beta I, what do they do here? Well, they obviously take a vector from V1 to a vector from V1 because they do not change anything here. So the fact that the vectors are orthogonal to V2 after applying this reflection is also like, it doesn't change this fact,
Yeah,
right?
okay. I think it's clear.
So
Yeah, thank you very much.
It should just prove that for any set of indices, the sum of corresponding simple roots is a root. So not the sum of all simple roots is a root, but any sum of simple roots is a root.
No, just with
It's
this.
like this tree, right?
Yeah, this tree. should-
well, if you have let's say like two roots that are not orthogonal, then their sum is obviously a root.
Yeah, of course.
And well,
Why?
just because the preposition.
Just A1. Yeah.
Зачем применять как извлеченный штат?
Она после четвертого, да? Логично. Да не надо, там вот это вот, там даже computation не нужно, там просто можно взять там альфа-1 и сказать то, что существует
Ну,
неортогональный
если не
вектор.
существует, то он
Да.
не ставит.
Если
А уже
существует, то
это
тогда
уже
reducible.
Да.
Потом для альфа-1 и альфа-2
Не, ну
точно
это всё
существует один,
формализовано,
который
понятно.
не ортогонален хотя бы альфа-1 или альфа-2. Потому что тогда оно reducible.
Так,
И
нам
вот
надо
так
договориться,
просто.
через сколько лекций.
Ну через 10 минут, да, наверное, да? Чуть раньше.
Сейчас, но мы должны были 10 минут назад
Да.
начать. Давайте через 5 все.
Серьезно? Фундаментальное утверждение следует из того, что на плоскости ничего нет. Система такой не так, оно нет.
Ну, а что не так? Смотрите, действительно это верно. Ты не веришь, это верно. Вот же есть теория в простых системах,
Нет, на плоскости я верю.
Если меньше, мне кажется, сумма этих двух, правильно? Что еще? Куча систем, напомню, вот эти, да?
Разве?
Вот эти разные системы, да? Вот эти две, сумма это вот это две.
Да верю, верю.
Все.
Есть же еще противная, большая. Где 12 векторов.
Ну, ничего, это не знаю.
Так, неортогонально. Что у нас? Вот этот, да? Что получается?
Ну, какая?
Не, ну, понимаешь, это дискриминационная задача, логичная.
Okay, so since we have not too much time, I wanted maybe first to say a little bit more about while group. So there's this notion of length of an element of while group, but it's kind of requires some also more technical, stuff about all this reflection. So maybe just to speed it up a little bit, I'll skip that for now. We'll see if we will need this for representation theory that I really would like to start soon. But for now, let's jump straight to Dynkin diagrams, classification of root system, reduced root systems. Okay.
We will need it for character forms, right?
Yeah. Well, if you know Bernstein-Gelfand resolution, then you don't need it, for sure. Like you don't need like all the technical stuff that is actually Kirillov is doing there, because like he's obtaining a lot of lemmas, and if you look further, they are not applied. If you don't go like too deep into BGG resolution, for example. So I don't know. We'll see. So we just had a lot of technical stuff. If we need, we will come back to the length. Right. We'll just try to do this way. So Dynkin diagrams. So let me denote by curly gamma the set of the following graphs. Denote the set of the following graphs. Vertices, there will be only one type of vertices. We'll just denote them. It just depends on the book or in the picture, just by circles. And you have three types of edges. So edges are like this. Either just one line, or two lines or three lines. Okay. But 2 and 3 lines, they are directed. So I have to draw an arrow. So this is just as it is. Let the gamma be the following set. All right. Dynkin diagrams are the following subset of gamma. So definition. Dynkin diagrams are the following elements of gamma. So we'll have, they are labeled by letters, A, B, C, D, F, and all the way up to G. A, B, C, and D are a series. So therefore we have for each positive n, I will have diagram AN, and it looks like this. It's just a chain of this sort, where I have n vertices here. Then I have bn's. Okay, so bn is this. So again, I have n vertices in a line, but then at the one of the n's, I will have double edge, which looks this way, oriented this way.
It's the last one.
The last one. Yes. So then we have Cn. So Cn is the following thing. Well, again, you have the same tail. So again, n here is the total number of vertices, including this special one that I have. And then again, you have double edge at the end, but the direction is different. Okay, dn again, you will have this, and then at the end, you will have something like this. Again, n is the number of total number of vertices in all of these cases. So n total number of vertices. So these are all the elements of this subset that I'm defining that come in series, in infinite series. All others are exceptionals. So I have 3 exceptional diagrams of type E. So E6, E7, E8. So they are kind of similar. I have 2 vertices. Then on the third one, I have vertex of order 3. And then how much should I add? Another 2, right? So then in E7 and in E8, I just add corresponding number of vertices to the right. So I'll have E7 is like this, and E8 is like this. 1, 2, 3, 4. Okay, E, then you have F and G. So you have just one F, which is F4. It is like that. And then you have G2. The only thing that has triple H, actually. That's it. So these are all. That's how nature is actually exists, right? So they actually appear in a lot of things. So in particular, in the classification of root systems or semi-simple algebra. So these are all called Dynkin diagrams. Maybe let us invent some letter for this subset. So maybe let's denote the subset of all Dynkin diagrams by I don't know, D curly D, I don't know. Yes, and so now I would like to relate this to root systems. So for a pair, root system and well, a polarization, or rather, I would fix simple roots. We can associate an element of gamma as follows. So edges represent simple roots. Why edges? Vertices, sorry. Vertices represent simple roots. And edges are given like that. So if I have two simple roots, if there's no, so edges. If there is no, so the edge that I put between two vertices representing two simple roots is this number n alpha beta, right? It's given by this number n alpha beta. So if no edge, then the edges are orthogonal, and alpha beta is 0. So if like this, this corresponds to an alpha beta being -1, right? But let me rather put it like this, so just all information that I can get out of this fragment of my Dynkin diagram. So alpha and beta, they are of the same size, so 1. And then n alpha beta is n beta alpha, it's -1, right? So for h like this, I have the next. So it's double h, right? So therefore, I will have 2 appearing here everywhere. So first of all, alpha to beta is square root of 2. So really arrow pointing towards the shorter root. Okay, so that's, and then n alpha beta is -2, and beta alpha is -1. And for triple H, we have alpha, the ratio of lengths of alpha and beta is square root of 3, and n alpha beta is -3, and beta alpha is -1. So these are the rules. So you're giving me R and P, I give you the diagram. Then I would like to observe that doesn't really depend on the choice of polarization. So if we actually proved in the last lecture that if I have two different polarizations, then they are related by action of W. And action of W is automorphism of, like, well group is a subgroup of automorphisms of R, right? So therefore, it respects all n alpha betas, and really the diagram that I get is the same. Okay, so that's our next observation. So notice that Rp and Rp prime give the same diagram. The same, well, of course, like my labeling of vertices can be different, but like isomorphic as graphs, right? All right, this is because P prime is W of P, where W is an element of Weil group, which is subgroup in automorphisms of R. Okay. Moreover, if I have isomorphism of R, then it, so if I have two roots two root systems that are isomorphic to each other, then again I will have the same diagram, right? Obviously, for the same reason. So therefore, I got the following map. Let's call it somehow. I don't know. Usually, denote phi. So from isomorphism classes of reduced and I would like actually to add irreducible here root systems. To where? To connected graphs in gamma. That's because relation between connectedness and so you did all the job, right? So of course, if it's irreducible, then the graph should be connected, of course. And the other way around as well. So if it's disconnected, right? If I obtain some diagram such that it's disconnected, then I started with reducible root system.
What do you mean when you say connected? We have some oriented edges.
Forget about orientation? Yeah, we forget about orientation. All right. So we have theorem which is the following. So first of all, and this we already almost proved. We actually proved it on the seminar. Phi is injective. And second is that image of phi is exactly Dynkin diagrams. Okay, so let's try to look at part of the proof. So it's a big, actually, one of the main.
Is it true that for any Dinkin diagram, its image equal?
Equals.
Slice?
Equals, yes. That's
I did the proof the first day.
okay, so let's prove and like, yeah, so proof. Let me give you left inverse, right? So for injectivity, I need left inverse map. So if I have some graph here that I know for sure it came from some root system, okay, then I can can actually restore simple roots, right? I know all well up to rescaling, of course, but I can give it to you. So left inverse of phi just looks like this. You give me diagram, then I restore simple roots, then I restore the whole root system by applying the while group. While group I know if I know simple roots, right? Because while group is generated only by simple reflections. So I take pi, I know all simple reflections, and then I apply all simple reflections to pi and get, like this. So this is the inverse map. And now let us look a little bit into the proof of this one. Right. So we would like to first try to look. Not the first, okay, so I'll attempt to at least understand what could be the arguments to prove. The second one will be only for simply laced. Simply laced, okay, this is some terminology, but by simply laced diagrams, people mean those without multiple edges. Yeah, ADE. So when you usually look at the papers, they say something of ADE type, and usually this means simply laced cases. Right. So So I'm not. We're not given to proof completely. Just look what arguments can be. Typical arguments can be made. So basically what you do, you prove that image of phi is inside, but then you have the pretty limited number of diagrams then. And for each, you can actually construct corresponding root system. Of course, it takes quite work to construct, I don't know, E8, for example, that we will not do. But this part, so the equality part, okay, we will not do. Well, we partially did it because we know some of these diagrams correspond to which root systems. Yes, yes.
We only don't know F4.
F4, E7,
Does we know AN, BN, CN, DN?
AN is S7, DN is
Bn is SO2n plus 1. Cn is SP 2n.
I think we
Yes.
didn't move for SP to N.
It's
We didn't prove.
from the quiz or that we had.
Yeah, but it's for SP4, isn't it?
Well, yeah, but you can.
Yeah, and Tn?
So to n.
Ah, so. And what about E6? E6 is 7, E8, and F4 we don't know, yeah?
Yeah, these are some exceptional constructions. Actually, this is what really mathematicians do. Because like sometimes I would like as math physicist, you usually deal with series, right? But like when you meet somebody really hardcore, they like, yeah, the whole mathematics is an exceptionally algebras. Which actually might be true. Yeah. Anyways, let us at least look at this, and we just try to look at all elements at all diagrams of GAM and try to, rule out some cases. Then we will end up that only thing that we can have is inside D. Again, assuming that for simply waste case, right? So it means no multiple edges. So it equals ADE, no multiple edges. And okay, so how to see that? The main idea is that, well, simple roots, they are all linearly independent, right? And if you try to consider some subspace which is spanned by subset of simple roots, then the corresponding Gram matrix should be non-degenerate at least. Okay, so that's the main idea of ruling out things. So it's not like there's no like some big conceptual trick that you need. It's like ruling out. First, you rule out a lot of diagrams. You end up with Dynkin diagrams, and then you just construct all cases by hands, kind of like that. So main idea to prove so a Gram matrix of this restricted to some V, where V has some basis. Well, Gram matrix is actually depends on this basis, right? So I don't know how to put this. So span V1, Vk. So these are linearly independent, usually will be. Is non-degenerate. So we are going to rule out first cycles in diagrams.
What is V1, Vk?
So I'm going to take some linearly independent vectors in my E, and of course, and compute this matrix, right? Vi, Vj. This will be ijth element of this matrix, and so this matrix should be non-degenerate at least. Okay, so that's if it's degenerate, then I cannot have some sub-diagram in my diagram. So that's how it works. So on examples, it will be more clear. So how to prove that there's no cycles in image of phi. So suppose you have a sub-diagram of a diagram from an image of phi, right? Some cycle. Alpha 1, alpha 2, and so on, alpha k. Then I just consider my v's will be alpha 1, alpha 2, and so on, right? And then my gram matrix, and also we assume that right, we can assume in simply laced case, right? So this means that n alpha beta is exactly this, right? If you assume, so assume that alpha norm of alpha squared is 2. So we would like to fix some scaling otherwise, right? Just otherwise we get something like something similar. So let's fix that all roots since have length square root of 2. Okay. Then my matrix corresponding to, so my matrix alpha I, alpha j is like that. So I have 2's on diagonal, right? So it's almost like your standard matrix for, so it's your matrix for affine assault, right? So actually, negative 1's here. So this would be Cartan matrix for SL n. It's okay, I don't know. Yes, but because of this cycle, you also have negative 1's here. And then if you consider just vector corresponding to of all ones, this will be in the kernel of this. Right. I find Cartan matrix, they have rank, co-rank is 0, actually. Right, so how to, sum of alpha i's belongs to the kernel of this matrix A. You can check, right? So the sum over all, you'll have negative 1 here. Sum over all rows is 0. So therefore, we prove that there is no cycles. Okay. Next, so let me maybe leave this here. Then I would like to see that there is no the vertices are of order at most 3. Okay, no crosses like this. Actually, yes. Well, dn is okay, but so no things like this. Okay, so in this case, mhm.
True that this proof like highly relies on the fact that this is simply waste case, right? Because when we talk about non-degeneracy of gram matrix, we kind of use that. We can say that all metrics have the same length, right?
Yes,
So
yes.
we don't have
So
to care about
in non-simply waste case, you need additional step. So it should be a product of diagonal matrix and symmetric. So it's some statement. So actually, any Cartan matrix that you have is like that, and you look at symmetric part. Yeah. And diagonal is still, you don't have zeros on diagonal, so it's still positive defined. Which is, I think it's clear right away, right? That it's positive defined. Anyways, so in this case, I do what? I do the following. So let me label this alpha, beta 1, beta 2, beta 3, beta 4. And then let me, so my Cartan matrix in basis, no, so we have alpha in this order: alpha, beta 1, beta 2, beta 3, beta 4. Let's see, right. Then the corresponding matrix will be like that. 2, minus 1, minus 1, minus 1, and then minus 1, minus 1, minus 1, and then 2, 2, 2. Not enough minus ones, I agree. One more here, not enough twos as well, but I can just dot it.
It's like submatrix of our gram matrix would be.
Yes.
Because it's like just a part.
Yes. It's a part of graph. And I would like to have something in the kernel, and looks like this should work. So this is 0.
Why is it? Yeah.
Okay, so for some reason, kind of didn't think about the case. What if I have 5 variants of the?
Well, it could be another minus 1.
Let's see. Maybe we can cook up something on the fly, but.
You can just forget about this.
Yeah, sure.
Submatrix here.
Yes, you're right.
Just can put 0 on the last.
No, I just, it's submatrix, we just cannot take this corresponding row, yes. Very well. So, this, but still, what if I have, this rules out a lot of things already, but not, for example, these things. So, no things, so this was number 1, this is number 2, this is number 3. So no things like like this. So where you have something like D2 but on, or Dn but on both ends. This is another, by the way, Dynkin diagram for a fine Lie algebra. So it should have some kernel. But let's see. So we have, and actually exactly a kernel of dimension exactly 1. So we would like to reduce it to this case and to have this beta 1, beta 2, beta 3, and beta 4. So what to do? So instead of all these alphas, I take alpha to be the sum of alpha 1 plus alpha 2 plus and so on plus alpha n. Then I claim that I have the same case. So if I take now consider alpha, beta 1, beta 2, beta 3, beta 4, they're still linearly independent, of course, right? But I just need to compute alpha with beta I in this case, right? So alpha with beta I, well, there's some computation, right? Or is it? No, this is just -1 right away, right? Just because there's only one end, and it works with just one beta I. So some computation is that alpha with alpha is 2, right? But this is just sum of alpha i's.
So I still assume that the length of each vector is square root of 2, right?
Yes. So this is, of course, squares, right? So these are, each of them is 2, plus 2 sum over I from 1 to n, right? So plus over all these edges, right? Alpha I plus 1, n minus 1 here, right? So this is -1, right? So I have n's of this, so it is actually 2n, right, minus 2n minus 1, so 2. Pretty easy. Okay, so now maybe less interesting part, which I'm not going to, some elementary computations, is that, okay, so now the only thing that is not here is that we have like this star with 3 rays, which go like for a long, like, so for example, I cannot like put something to here. So how to see that?
What about the third case? Did we deduce the second one?
Yeah.
Yes, we did. So alpha with, this alpha is the same as alpha, the sum of alphas here. Because the only thing that was that I need to check is that alpha with itself is 2, and that alpha with betas is -1. Then I give just the same matrix is there.
Yeah,
That's yeah, that's a good question, and it comes from very dumb calculation. Actually, I don't know. When I was first, encountering this, I was like so excited. Like, what's the secret, trick to see all this? And then people just said, like, you just, go case by case and then rule out something. So like, yeah, I don't know. It's kind of mystery still.
But the
It's
reason
like
is still about is in this degeneration of matrices, right?
the reason is.
So do we need some new methods or just make matrices and
Let me actually recall. No, this one is just some triangle inequality. So let me be more specific. So suppose I will just give you the inequality that will rule out all others, like all these things that you would like to draw there. Okay, so I would like to draw something like this. So I will need some condition on how long can I go. So let me denote the middle one by alpha, and then the branches by beta, gamma, and delta. So here I have beta 1, beta 2, and so on, all the way until the last one is beta, whatever, p minus 1. Right, so I will have some inequality for p, and then here I will have delta 1, delta 2, and the last one is delta r minus 1, and here, since I skipped it, so gamma 1, gamma 2, and so the last one is gamma q minus 1. So I will need some inequality for p, q, and r. And it actually comes out of the following. So you actually denote beta to be sum over I from 1 to p minus 1, and then I beta I. Gamma is sum over I from 1 to q minus 1 I gamma I, and delta is the same, I delta I, and you just see that, well, first of all, if you add alpha to it, then these 4 vectors are orthogonal, so they're linearly independent. And this means basically that projection of alpha to these 3 vectors, to the plane that is spanned by these 3 vectors, is shorter than the alpha itself. Okay, for sure. So inequality is like that: alpha beta over beta square plus alpha gamma over gamma square plus alpha delta over delta square less than alpha square. nothing too fancy, but if you just compute it all in terms of P, Q, and R, then you'll get 1 over P plus 1 over Q plus 1 over R is less than 1. And then you just, try to, if you would like to have something bad, just plug into here and see what that rules it out. Right? So for example, E, what? Let's maybe check something like, or maybe let's just not do arithmetics. Okay. So I have nothing else to say about classification of root systems. Now we need to say that any reducible root system is actually this corresponds to some simple Lie algebra. If not irreducible, then semi-simple. And the other way around. So this is another big theorem, actually, that we're going to see. Okay, so any other comments? So your comments are always very good. So what?
Well, we were just talking about how this inequality is obtained. It's some kind of Pythagorean theorem, or
I would call it a triangle inequality, but which is not triangle, but rather.
Well, it's some kind of.
It is triangle inequality. Well, if you project one vector, if you project a vector on a plane, right, then it becomes shorter. That's it.
Isn't it for 6, P should be equal to 3, Q should be equal to 3, and R should be equal to 2, yeah?
E6, 2 to 1.
Yeah, but that's P.
Yes. Yes.
P3, 2. So it's like 1/3 plus 1/3 plus 1/2. Isn't it larger than 1?
Okay, so let us see. Maybe we have some mistake. So we have indeed 3 E6, right?
Yeah.
3 3 2.
Yeah. So like
It's like if we cannot take more than we cannot take it the third one. The big it is not about inequality.
No.
it should do R. Like
Sorry, maybe I'm mistaken.
yeah,
Maybe more, yes.
more than 1.
Right. Because I have D and I have a lot of. Wait. So for D I have smaller and
We don't
smaller.
have big P, Q, and R. If we have
Yes.
big P, Q, and R, then this equality is satisfied.
Yeah.
So we need to
Okay. Yeah, so maybe I just wrote it down correctly
How
like
it's
this.
working. So it should be.
No, okay. Let me.
Working, but
Let me. Sorry. So. Just to make sure that I didn't write something. Just let me check.
Maybe if we multiply it by QR, it's like QR plus. No, it's not possible.
it's like 3 less. I don't know.
There is no way to guess the formula.
Oh no.
Yeah, it's not like it's Yeah, it's greater than 1. Yeah.
And how it connects with the
And so how it connects to what?
to the like
Yeah,
the last
to this one, well, you actually, what is obtained exactly from this one is p minus 1 over p plus q minus 1 over q plus r minus 1 over r less than 2.
and how you will get
And then,
What's the reason with minuses? It's because it's 3 minus.
yeah, well, we can try to do arithmetics, yes.
yeah, of course.
Yeah.
From there, it's obvious, yeah. Because
Okay, so now how much time? We have 20 more minutes, so maybe let me talk about now length of the while group.
we
Since
have like 7
do we?
It's not. Yeah, it's 5:40.
Okay.
Maybe
Ah.
we start.
Yeah, so let me just define. Because next step is to talk about serial relation. I think it's good to start fresh next time. But this one is just serial relations. We're going back to simple algebra. So this was pure root systems, right? Another pure definition about root system that is quite fundamental is the length of so maybe the length of an element. All right. So by definition, the most natural one, it's not like what's given in Kirillov, the length L of W of an element W of a Weyl group such that it's not an identity is defined, so is a maximal, is a minimal possible natural number such that W is written as a product of simple reflections, SI1, SI2, SIL of W. Right, so here Si is S alpha I, where pi is alpha 1, alpha r. And one important instrument that also, so this is a well-defined notion, and it comes from time to time when you talk about root systems. So good to know. One proposition that it's kind of technical to prove, not in 5 minutes, of course, is that you can compute this L of W by as following. It is number of those positive roots such that if you apply W to it, it becomes negative. Okay, let me see. Maybe I will not prove that in a couple of minutes. Let me just maybe we can discuss it next time for some short amount of time. But let me just discuss a couple of corollaries that comes out of this proposition. So corollary 1, do we want to erase all this beauty? I don't know. Let's. Is really immediate corollary 1. But still very useful. So if I take simple reflection, then the only so consider so actually Si permutes the following set. It's all positive roots except alpha I, because alpha I for sure goes to negative alpha I, but all others stay positive. This is clear from the proposition, of course. So L of W is 1. So there's only one root. And this is exactly alpha I. Yes. So corollary 2 is action of the while group, so W action on Weyl chambers is simply transitive. So it's transitive, we proved that. Simply transitive means that each Weyl chamber is connected by unique element from the Weyl group. So not only they are related by an action of some element, but this element is unique. And this is proved like that. Again, it's corollary of this proposition.
It's the same as there are no elements of Weyl group that act.
Yes.
One on the Weyl
Yes, this is the same. Yes. So since you said it, I skip this implication. So this equivalence. Okay. Well, well, okay. Let me not skip. So suppose that C1 is W of C2 and C1 is W tilde of C2. Then C2 is actually some U of C plus, right? Let me plug this into this thing. So I have actually W U C plus, right, equals to W tilde U of C plus. Let me denote R to be something. What? W tilde U, W inverse, U inverse. So then then R doesn't change C plus. Okay. So then, it means that I have an element that doesn't, such that C plus is invariant with respect to this element. I don't know yet, by the way, that it doesn't move this at all, but it's actually true. Actually, it's true that the Weyl chamber is a fundamental domain of this action. Anyways, we're proving this. So I take some T from C plus and alpha from R plus, right? Then RT is again in C plus. Then RT alpha is greater than 0, right? Therefore, T T R inverse alpha is the same thing as this one. But then it means that R inverse alpha is positive, because I took T from C plus. And this is for any alpha from R plus. Therefore, L of W is 0. Therefore, not W, sorry, R inverse. Anyways, it means that R is identity. And then it means that W equals W tilde. Okay, and corollary 3 is that we actually have an element of maximal length. It's called the longest element of Weyl group. It's also a quite fundamental notion, and if you work like with Lie algebras, it comes a lot. So let me. This will be the last corollary that do today, and then we'll formulate proposition. No, I'm joking. All right. So corollary 3. So let W not be defined by the following. So I take C plus and apply W 0 and get negative of C plus, which is also Weyl chamber. Since by corollary 2, this defines me an element of Weyl group uniquely. Then for every W from W, L of W less than L of strictly W not. Okay, proof. It's kind of similar. Take again T from C plus, alpha from R plus, right? Then I take W naught inverse applied to T with alpha. So negative C plus applied to W inverse is C plus. So therefore, this is negative root.
I suppose you should say that W.
Yeah. So I'm sorry. So this is from negative C plus.
Why?
Because T is from C plus, and I applied W0 inverse, it will be from negative C plus.
Ah, yeah.
So therefore, this is less than 0. And then this is T W not alpha. So therefore, W not alpha is negative. Right? This is for all alpha from R plus. So this means that length of, if I take just the same reasoning, okay? The same computation, if I take some other W, I can find some alpha such that this equality will be different. Right?
So W is some element of Veil group that brings C plus to C minus, right?
Yes, unique element.
Yeah.
W0 is such
How
a.
do you
W
define
is
W?
just any element.
W is any element. No, okay, that's finished. It's just a couple of lines. So let me take now W, which is not W0. All right. Again, this means that W, I just have not equalities, right? C plus is not this, right?
Why W inverse?
It doesn't really matter. I can minus can go either way. Yes. Just because I would like some alpha in R plus, right, such that W inverse T, right, T is from C plus, alpha is greater than 0. This means that T W alpha is greater than 0. Therefore, W alpha is positive. So there exists some alpha which does not change to negative, some positive which does not change to negative under action of W. So this means that, yeah, sure.
Why W inverse can't take C plus to minus C plus?
Say it again. Sorry.
Why W inverse can't take C plus to minus C plus? Why this inequality holds?
Well, because this, suppose it's true,
Yeah.
right? Then this means that W of C plus is negative C plus, and then it means that W is W0.
Oh, it's like we. Okay. Yeah.
Yeah. Yes, very well. So this means that L of W is strictly less than this number, and so we are done. And that's it. Okay.
So the length of this word is R divided by 2.
Yes.
What is this word?
So in this, so it gives us the lowest weight. If you start with highest weight vector, give us lowest weight vector. It's just in S3, which is W for A2, right? It S2. Sorry. No, S3.
What is this?
Right, so you have S1 and S2 there. So then W is 1, S2 is 1. S3 is a permutation group on 3 letters. So I mean, you have A2, right?
Yeah.
Then you have some. This is your main well chamber, right? Then you get. Then you get reflection with respect to S1 to here. Then then to S2 to here, and then with S1 to here. So it gives you
No. S1 is not it.
This.
No, I think you should. S1 is vertical.
So S1 is vertical.
So to there.
Then I'm confusing something. Sorry. So I really would like to end up in C minor. I would like to end up in C minus.
S2, S1.
Yes, like this. Sure.
But in the not like firstly S2, then S1. So S1 is 2 actually.
But it doesn't.
Maybe you name the vectors, so
The second reflection is not correct.
Okay, so without this.
Where is S3? S3 is what it is. So we take by S2.
So this is.
Where is positive chamber?
Well,
So these are simple roots I'm writing. Alpha 1, alpha 2.
Yes. Then positive chamber is to the left.
This one.
But the second reflection, it was. It was.
yeah. The second reflection
Is bad, right?
It's not it. It's not the second reflection.
So okay, this is S1. Then S2 should be with respect to this one. So I end up here,
here.
and then S1 again. Yes.
So you
Okay. Yeah. This I know kind of know by intuition. So but yeah.
for S3 it is also something. It is also something linear.
Yes. So it's also related to Coxeter groups, and you have like this. So Coxeter relation in S3 is S1 S2 S1 equals. So it's how's it called? Braiding I think relation. Yes. But really it means that S1, S2 to the power something, yes, is 1. And this number here is related to n alpha beta somehow. And this is really Coxeter relations, what's called. And because of this, you have actually the maximal length that you can achieve.
For SLN, it should be SN, and in SN there is always something like that. So
Yes.
Something like mirror. It is a mirror reflection. One to n goes to n.
so we like in one plane we mirror reflect, then in another plane we mirror reflect.
No, if we in SN it is permutation 1 goes to n, 2 goes to n, minus 1 and so on.
In SN, with the while group for SLN, you have the longest root. In this case, it's alpha 1 plus alpha 2, so it's reflection with respect to the longest root. I think it's not quite like that in other types.
Это же последний юцис получается.
Ну да, такой раздвинутый максимально.
Докажем то, что полупростой алгебре есть.
Вот это вопрос.
Что-то мы слишком далеко зашли уже.